Hello and welcome everyone to NetAlly's Tech Chat. My name is William Petrovich, a product manager at NetAlly, and today we have a super special guest with us, Mr. Peter Mackenzie. Hey Peter, how you been?
Yeah, very good, thank you. How are you? Have you been?
Oh, pretty good, pretty good. Always busy, you know how it goes.
Indeed.
So, Peter, before we get started here pretty quickly, and I allow you to introduce yourself, a few very basics for everyone here. So,
Yeah.
guys, we like to keep these sessions interactive. So if you have any questions or you have any comments or you want to share your own example with us, then hey, feel free to type it on the chat. I'll read those and hey, we'll go back and forth and have a conversation here. After all, it's a tech chat in itself. Then Peter, just for those that don't know you, even though I suspect a lot of people here knows who you are, but for those who don't know you, can you give a little introduction on who you are? What do you do?
Yeah, sure thing. So my name's Peter Mackenzie. I'm from the UK. I work in the UK with a company called Marquest, where we provide lots of different networking support services, specializing mainly in wireless networking, but also in particularly in sort of troubleshooting and analysis. I've been working with protocol analyzers for, I think, probably about 22 years now.
Oh, wow.
So it started off doing a lot of wired analysis. Then around 2001, got into Wi-Fi and started working doing a lot more wireless protocol analysis. And I'm a complete protocol geek. I love protocols. I love looking at packets. That's how I learn technology, by looking at the protocol. So that's me really. And you know, that's what I'm hoping to share a little bit with you guys today, is a bit of sort of protocol analysis.
Well, thank you, Peter. For those that don't know, when Peter says that he really likes packets, he really, really means that. So it's not like it's a joke or anything for this session. He really likes this stuff, and we'll see that in a few moments. Now that I think everyone knows who you are, well, I guess we can get started here with the topic at hand. And Peter, it sounds like today you'll be sharing with us a few examples on wired problems that cause Wi-Fi issues, but mostly focusing on TCP/IP and QoS. So what kind of stuff have you seen out there?
Yeah, so I've seen a whole load of stuff out in the wild. And I think one of the things that is always good to remember now is when you look at how do people connect to networks, the primary connection method is Wi-Fi. That most users are going to connect, and that's just increased since the pandemic, because everybody needed a laptop to work from home. So even if you're heading back into the office, you're connecting wirelessly. So what that means realistically is that every problem is a Wi-Fi problem, but does that mean it's an RF problem? But very often not. It just means all network problems to the user is a Wi-Fi issue. But actually, all those problems that we would have considered wired problems are now wireless problems, or often fall to the Wi-Fi people first to troubleshoot. So I think what that means is, especially in my job of going out and troubleshooting, I often get called out to fix Wi-Fi problems and end up fixing wired problems. And I've seen that from fixing, you know, misconfigured firewalls to problems with, you know, internet handoffs, to a whole host of issues that were relying on the wired network. But that wasn't necessarily the initial diagnosis.
Hey, so quick question. Percentage-wise, I know I've always been curious about this. How percentage-wise, how many of the problems you actually see out there are actually Wi-Fi versus just wired that basically translate over to the Wi-Fi?
Yeah, it's a really good question, actually. I would probably say, at least from my job, and one thing I always am very mindful of when I give sort of my opinion on these statistics is that it's one thing to understand is that the problems I see are probably not typical problems, because if you're going to phone a consultant and pay them, you know, obviously I'm very expensive, pay my rates to come in and fix a problem, that's not normally going to be your first line of attack. The minute, you know, a user phones a help desk and says we've got a problem, people don't go, right, phone Peter up. They'll try and fix it themselves, obviously. Yeah. And companies have, you know, they have Wi-Fi engineers, they have network engineers, so they normally go through a process of trying to fix a problem before I get involved. Okay. So generally the problems I see are the problems which people haven't been able to fix. Okay. So I like to say that, because therefore my view may not be normal. But out of the problems I see, I would probably say it's about 50-50.
Oh, interesting.
I would say that when I've been called in particularly for a wireless issue, probably 50% of the time it's a wired issue. So when it's been perceived as a wireless issue, sometimes I get called in to fix Wi-Fi wired problems particularly, but obviously when it's perceived as wireless, I would say probably about 50% it's time it's not.
Yeah, that's an interesting statistic, and I guess you shouldn't be surprised. A lot of people sometimes forget that there's always this wired backend to a wireless network. So that impacts basically anything on the wireless side. So we have a question here, even though I'm not exactly sure it's related to what we're talking about right now, but I'll ask it. So from Germund, what is the usual MSS size in the TCP header from mobile devices when Wi-Fi is used? My Samsung S10 uses 1250 bytes.
Yeah, that's a good question. I'm not sure. I think you do have to look. 1250 actually isn't a totally normal amount, but different operating systems, different devices will actually have different maximum segment sizes, which is quite interesting. You know, typically the MTU, which is slightly different to the maximum segment size, is going to be 1500 bytes. So very often when you'll see a smaller maximum segment size below that, because it's allowing for your IP and TCP headers.
Okay, cool. So again, that's the question we had for now. So Peter, I know that you have some cool examples that you want to share with us regarding some of those issues you've encountered out there with TCP. So let's just start sharing the first one. And what weird stuff have you seen out there?
Yeah, one thing I was going to just say before I share its first example actually is, so when I get engaged in a troubleshooting engagement, so someone comes in to troubleshoot and a wireless, I'm going to talk about wireless issues here when people come in for wireless issues. This might surprise some people, but the first thing I do when I get on site is I set up a wired capture. Okay, and I always set up a wired capture, and I leave that running, and then I might do my wireless captures and I do all my analysis, follow clients around, try and see the problem happening. But I've got this wired capture running all the time in the background, and the reason for that is for exactly what we've said. Is you can look at do your wireless analysis, and if you find a problem, great. You maybe never look at the wired capture, but when you determine actually the wireless is okay, then where do you go? So yes. I always have this wired capture running, and I'm a big believer in that approach. And now where do I have it? Well, it depends a little bit what the problem is. Could be behind a wireless LAN controller, behind an AP, monitoring an application server if it's a particular application that they're having problems with. So it depends what the issue is, but I always have some wired capture running. And the first thing I've got 3 examples I was going to show you. One of them is a Dhcp issue, which I'll show you first. So then I'm going to show a more in-depth TCP issue, because we said TCP. And then I thought I would show you, they're both going to be looking at sort of wired side analysis mainly, a bit of wireless. But then finally I thought, why not show we're going to talk about looking at detecting sort of wireless issues from a wired side. Why not show you the reverse, how to detect a wired issue from a wireless trace file? And that's the QoS example I'm going to show. So they're the 3 examples I'm going to show. So let me share my screen, and then everybody can hopefully will see what I'm seeing.
Yep, got it.
Is everybody seeing my screen? And you should be seeing my protocol analyzer, hopefully in front of you. Now, I'll give you a bit of background behind its first issue. It was the complaint was that sometimes some users couldn't connect to the Wi-Fi. That was a complaint. Sometimes users couldn't connect to the Wi-Fi. And as we went round with a user, what they were trying to connect in different places, and they had an issue, we noticed very quickly that there was a little explanation mark when they couldn't connect via on the Windows, saying that they didn't have an IP address. So no protocol analysis needed for that. I could see that, but why did they sometimes not have an IP address and sometimes they get one? That was the question. Because probably the majority of users, the majority of the times connected, but sometimes they couldn't. So that was the so to look at that, we decided to monitor basically all the DHCP traffics behind the AP we're trying to connect. And that's basically the trace file I'm showing you here. So you'll see in the application, we've got DHCP. These are all DHCP packets. And we left this capture going all the way until we got an issue with a client. So you'll just see I've got literally loads of packets. But towards the end of this trace file, near the bottom, you can see where there's an obvious problem happening. I'm even seeing it here saying DHCP request rejected. So, and the actual DHCP message that causes that is something called a NAC, a negative acknowledgement or a non-acknowledgement, sometimes people call them. But it's basically in the process, we have a client requesting the IP address say let's had. A request comes in and the DHCP server says, no, you can't have it.
Okay.
So that's all very interesting, but why? That's where we need to dig a little deeper, because I can see that some people up here request acknowledge. Further, a bit further down, we're getting something. So it wasn't happening all the time, which is what was the behavior the users were telling us about. But sometimes we've got one here and I've got one here. So I'm going to dig into the packet and see if we can find out why is this issue occurring? Why would it sometimes reject it? Now, one of the things when people start seeing this is that the default answer I think a lot of people jump to is that the DHCP server is running out of IP addresses. So it's going, nope, I don't have it, or I've assigned it to someone else. But we did ask the people when I first saw the explanation mark, have you got enough IP addresses left? And they checked their scope and they said, we've got plenty. So that wasn't the case. So we've already ruled out the obvious here. There's something else going on. Now, when we look at a DHCP message, you'll get a whole host of information in here in the message type. Now, one of the things, and the thing that I'm going to draw our attention to, is the server identifier. Now, that just tells me which DHCP server is sending its message. And one thing I like to do to make protocol analysis easier is to take some of these fields and put them as columns in my in the packet view, so I can see is there a difference between an ACK and a NAC. So we're going to do that with this address field. So I'm just going to say add as decode column, and I'm going to come right back over to my packet view, and we have got the address here column. And once we do this, something became very obvious to me. If we look at all the ACKs, 10.104.32.2 was the server, but when we got a NAC, it was coming from 10.104.32.1. And that seemed to be the big difference. So why would they you know, a different. So that led me to ask the obvious question: what is your DHCP server address? Do you have two? And they said, oh no, 32.2 is our DHCP server address.
Okay.
So why? So then, of course, I asked, well, what is 32.1? That was a really obvious answer. And they went away and they came back and said, oh, that's our main switch at the site.
Okay.
Oh, it's a switch. So why is your switch sending DHCP next to certain clients? So of course I asked the question, do you have, what do you often run on a switch? You can run DHCP helper functions if it's a layer 3 switch. So that was my next question. Do you have any DHCP helpers? They said, oh no, we don't. So I said, could we look at the config on the switch? Because I wasn't believing that. And as we looked on so they brought up the config, they did a show run for me, and sure enough, there was a DHCP helper function on its switch. And it was sending messages off to another DHCP server at the head office, routing it off, which didn't have this subnet in scope. So it was obviously rejecting it because it wasn't going to the local DHCP. And it just seemed to be that how DHCP works, because it's broadcast. If the switch happened to get a response first, the client didn't get an IP address. If the correct DHCP server managed to respond first, it got an IP address. Hence a completely random situation where sometimes they got an IP address, sometimes they didn't. So an interesting little problem.
That is indeed a very interesting one. And regretfully, as I asked many times, it seems like it was a configuration problem. So it must be a human created or the piece behind the keyboard type of thing. Someone made a typo there.
Yeah, I think it was an old piece of config left on a switch that just never been removed, and it just needed to be removed. So once we removed that helper function, no more problems. So that was a nice little simple issue, I thought, to begin with. The next one I want to look at is a little bit more.
One question, Peter, before we move on here.
Yeah, let's have a question.
Yeah, so Brandon is asking, what are you using to capture your packets? Is it a standard laptop, dedicated hardware? What about wireless packet captures?
It's a great question, actually. What do I use? Well, most of the time I'm using standard laptops because they're portable, going in as a consultant. So both for wired and wireless capture. But I do, when we have a requirement to capture above, so from a laptop gigabit Ethernet port, you're going to probably be able to capture a maximum utilization of just a standard built-in NIC card of about, I would say, 600 to 700 megabits per second on a high-end laptop. That's going to be maximum. So if if what you're capturing goes above that, you're going to start dropping packets. So beyond that, you can get dedicated capture cards, which you can run on servers. I do actually have a 10 gig capture appliance, which if I needed to monitor a 10 gigabit link, which I would probably be putting a tap in place to do that into my 10 gig appliance, you can do that. These things tend to get quite expensive, so they're not everyday tools, but you can do that. But for most of the time, because I'm looking, I know roughly what I want to look at, and I'm normally looking on no more than a gig link, which normally wouldn't be more than about 60% utilized. Laptops are generally okay. And I'm normally just getting my customer to mirror a particular port on their switch to give me the wider traffic.
Okay, great. Thank you for that. And I think, well, we have one comment here from Joe. It says, I noticed Peter is using OmniPeak. Do we get that same information on Wireshark? Yeah,
it's a great question, actually. Yes, you do. You get the same information on Wireshark. I like OmniPeak. I find it very user-friendly. I've been using it for over 20 years now, so it's a tool I'm most familiar with. Having said Wireshark, you can probably do most of the, I don't think anything I'm going to show you today you can really do with Wireshark. It might be a little bit, some of the color coding that I would probably show you, you can quite do with Wireshark in the next example. just to make the analysis a bit easier. But the full packet decode is exactly the same.
Okay, great. Well, those are all the questions we have for now.
Brilliant. Well, let me show you this next example because it's interesting. It was actually a problem in a warehouse. There was some voice picking devices. Voice picking devices are devices that they use to go around the warehouse and pick products that are going to go on the trucks. And they say a number. They get delivered a number to their voice headset of which product to pick. So it might be 9672. They walk to where 9672 is, that product, and they say the number back, and it says pick 4. And then they pick 4, and they say pick 4, and it gives them the next number, and they move on around the warehouse, the pickers. But in this particular warehouse, they were getting delayed responses. So they would say a number, and it could be 6, 7, 8 seconds before they get a response, which doesn't sound long, but it's actually quite long. You go 294, and you're used to having someone come back straight away. And after a second, if you don't get a response, you get a beeping, beep, 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 which says it's an issue. And it slows the pick down, and warehouse staff have to have a certain pick rate. And so they were getting these issues of several seconds of delay. So I went in, I set up my wired capture and my wireless capture, and I've got both captures here I want to show you. And the blame, as I always say, is the wireless network. So was the wireless network bad in this particular building? Well, I want to be honest that it wasn't great. That's why I want to start with wireless, and then we're going to go to the wired capture. So if just very quickly, I'm going to show you the retry rate on the wireless, which we're looking at here. Now, this is just looking at one client's traffic. So, but you can see how it's peaking up to 100% retries at times.
Wow.
So we're not, you know, it's often, it was sometimes down at 25%, sometimes. So there was a lot of, it was a very congested, lots of CCI, not an ideal, APs 15 meters high on the ceiling, lots of them, lots of clients. It was very congested, very busy, lots of retries. But was that the problem? So just because that exists doesn't mean it's a problem. Okay, so that's why I'm always a big thing with analysis is you may see something, it doesn't mean it's causing it's beeping, you know, because this environment has probably been like that for years, and they've not necessarily had problems for years. So was this the cause of the problem? It's a good thing to note, but was it the cause of the problem? Well, what I'm going to show you here is just one particular message that was sent and a response. Okay, and it was, and without going into a lot of detail, I put the actual from the decode screen the message in a column. Again, you're probably not going to understand that message, but it's a message that one of these devices send back. It's sending this message here back. It's like a get contour. It's saying give me a quantity basically for this product number here. So that's a message, and we can see, I'm going to give you a little tip here in its flags column. A plus is equal to a retry, okay? Retransmission. So I will also just put my color back to normal for a second for you. So this was the first time it sent a message. Now, something I've done is I've got my client and my app server, and I've called my client and my server side just to make it easy. And something we can do in OmniPeak, this is one thing you can do in Wireshark, is I can say color by source. So whatever the color is. So now red packets are coming from the client, blue packets would come from the application server. So we can see that we send the message and we get no response. We don't get even a TCP ACK back, a Wi-Fi ACK back. So it gets retransmitted. That's the plus. Exact same packet. And so we can see that there's a lot of, and look how many times it retries it, transmits it. And the data rate's dropping off and off and off, which is what you would expect in Wi-Fi. It tries at a high data rate, and the data rate goes less and less. So we're seeing normal wireless behavior in an unstable environment, but at some point, the AP sends an acknowledgement.
Yeah.
Great, it's got it. The client doesn't see it because it carries on trying to retransmit it. So it tells you how busy and noisy. So I've seen it as my analyzer, client hasn't seen it. And we get loads and loads and loads of retransmissions. And then this is something I'm going to quickly show you. At this point, we still haven't got an acknowledgement back. And I want to show you this little relative time column. I set the packet as that very first packet we transmitted. And you can see the time counting up. And then 0.2 seconds goes by, nearly 3 seconds off from this, and we get the same message again. There's a bit of a gap. But if we look at the IP identifier, which is every packet that a device sends out, it sends a unique ID. All of these retries were the same. 6283. Now it comes to 685. So while it's the same message, it's what we actually call a TCP retransmission. It's the TCP stack is resent, the device is resending the message. It's not just a wireless retransmission. So it's failed so many times, we actually need to do a TCP retransmission. You can see that mentioned here. So it's actually it's the TCP stack has gone, well, I'm not getting a NAC, so I'm going to retransmit it at a TCP layer. So we've got wireless retransmissions, TCP retransmissions. So one thing we can say is the wireless environment is pretty bad. This is all happening in less than a second, and the delays they're having 8, 7, 9 seconds. So I'm not convinced yet that any of this is my problem. Okay, I want to say the Wi-Fi environment's bad, and eventually, as we come down here, here because is the responses. So we do eventually get a response back after about 3 seconds. Then we get a response back again, the same response again. Again, it's retransmitting. But then eventually, that because something's not happening, we're getting a TCP retransmission of the response after 9 seconds. Oh no, so that sounds like where the problem's coming, but I'm not convinced. Why are these delays so long from the response coming back from the server? That's why I'm going to look at the wired side.
So one question here before you move on to a wired side, well, a couple of questions really that came in from Germund. On this last example, you said you captured on the Wi-Fi, so it is probably, at least he thinks, PSK authentication. Will your software de-encrypt the traffic while the client roams between APs? I do assume the PSK is installed in the protocol analyzer.
That's exactly right. Yeah. So this has all been. You actually notice it's called wireless client decrypted. This traffic. I put the PSK in here, so it's decrypting all the traffic as we go. So that's exactly right. The actual very beginning of this trace file, you just see encrypted frames, and then on the first roam of the client, when I call the authentication and the 4-way handshake, then all the traffic has been decrypted.
Nice.
Decrypt it with the 4-way handshake. So yes, and that's the reason I can see this message is because it's encrypted.
So one more question there from Trey in this case. What would you consider to be a normal range for retransmissions, such as for a hospital deployment with normal noise floor and normal ceiling height?
Yeah, so that's a really good question. This was a really noisy environment, but in a cleaner environment, so let's say you're in a really clean environment where pretty much it's just your network and there's not really many neighbors. I would normally like to see retries around the 10% mark. No, that's normal. You're going to get that in a really clean environment. You're going to get about 10% retries. If you start being in a multi-tenant, you're in a city center, they may probably go up to 20, 25% retries. If you start going above 25%, you're going to start to think that there's something causing that.
Okay.
There's some reason for it, but not very good design. This wasn't a great design. I say all the APs were high on the ceiling, way too high. There was too many of them, were too high powered. So you're going to start to think through those sort of environments. There could be interference if you're getting a high number of retransmissions, but that's the sort of roughly what I would say. So, you know, ideal scenarios, 10% or less. If you're going to get, you're always going to get some retries. So if it's a more busy environment, you may hit 20, 25%, and there's nothing you can do. It's just because the environment's busy.
Yeah. Yeah, I agree with that. From what I've seen, I think at 10%, it's about an average. You'll see a normal environment there. So one comment from Germund. TCP often do retransmission at 3 to 6 and 12 seconds, while Wi-Fi retransmits as soon as the Wi-Fi BA don't come back. So I'm guessing he just wants to add that to the conversation.
Yeah, so well, that's really interesting. Is how soon should TCP retransmit? And it generally, you know, any protocol really, you don't want seconds of delay. Generally, you want it to be generally milliseconds. If we have a look at this first, what the wireless device, its TCP retransmission was in 0.2, well, about just over 0.2 seconds. That's how long it took it before it did a TCP retransmission, which I think is quite reasonable. It's not as fast as the Wi-Fi retransmissions, which was happening in, you know, nanoseconds almost. You know, at that time, this was in, you know, in milliseconds, but it was in a 0.22 milliseconds really. It was in a TCP retransmission. So I think that's quite reasonable. You're not going to really notice that so much as a user. But the server is what interests me the most. Let's hop on to the wired side and see if we understand what we see on the wired side. So this is the same conversation. I've got the same message here. Now this was the original message. So when do I think that was sent? Well, I'm expecting from the wireless one. Remember, we saw all the retransmissions, but then we did see an acknowledgement from the AP. So at that point, the AP said, I've got it. So it's going to forward it on. Now, we don't think the client got this one, so it kept retransmitting, but the AP received it, so it'll forward it on. So I think that's going to be corresponding to this first message. And what does the server do? Well, again, I've set this as a relative packet, 0.04 seconds, so really quickly, it sends the answer back, the reply. So it was straight away. No problem with that, except we know that the AP kept resending its message. It didn't think it ever got it. So eventually, we see after 2.9 seconds, this is the TCP retransmission, because the AP is not going to resend the same message. It's going to eventually gets the TCP retransmission of that message and sends it over. So the server, even though it's replied, has just got the message again. And I think that's what slightly confuses the application, because it's like probably in some sort of state machine, it's how often these applications work. And it thinks I've already sent that message, so it's waiting for the next one, but it's got the message it's replied to again. And it takes it 3.1 seconds to reply, which to me is quite a long time. But we know from the wireless trace that this message never gets delivered to the AP. And it then does a TCP retransmission, but 6 seconds later, which actually is quite a long time before its TCP stack. So it's waiting for TCP acknowledgement for 6.1 seconds before it does anything, and then it resends it, and then this is the one that gets acknowledged by the client, and now we have a total of 9.2 second delay. So where's the problem with this network? There's sort of issues on the wireless, it's unstable, and those wireless issues are causing the application, I think, to get in a bit of a mess, because it is getting all these, but the application seems to respond really slowly at a TCP layer. Like I think 6 seconds is probably a long time. So if you could get rid of if you could fix the application so it responded faster, you probably wouldn't notice the wireless issues. Or if you fix the wireless issues, it probably wouldn't cause the server to get confused. So here's a situation that is born probably because of both Wi-Fi issues, a combination of the wireless issues and the wired server causing an issue. And you could actually probably fix it either way. But the combination of both and these really slow responses from the application server is what's actually causing these really long delays. Because actually on the wired side, the wireless retransmissions are happening fast. The wireless client is TCP retransmitting fast. It's just a server that's been slow. So in one sense, you point the finger at the server, but it's getting into that state because of the unstable wireless environment.
So this is a pretty interesting case. So how did you, well, which way did you go to fix this one?
So with this one, we actually sent it off to the application team because to fix their wireless environment was pretty much a full redesign. Dropping the APs lower. It was a lot of work to fix their Wi-Fi. And actually, you look at these messages. These are telnet messages. It's tiny, small bits of text sent infrequently. It's not a busy network. So actually, yes, there's lots of retransmissions. Yes, it's a bad environment, but they can get these messages through in a timely manner still, even though it's not a very nice RF environment. They are still pushing enough data. That the problem is, what we needed to do was speed up these TCP retransmissions, and that's what we did on the server.
Nice. And how much of an improvement did you get after that?
Yeah, no, we saw a big improvement actually from that. You know, this beeping that they were receiving just went away.
Oh, nice, nice. Wow. Well, and then you can see, guys, that sometimes there's not only one root cause of the problem.
Absolutely, yeah. It's why I like that issue. It's not just one root cause. It was, and it also shows, I think, why it's so important to look at TCP as well. And a couple of things just to point out here, which might be interesting to people, is you've got let's have a look. The IP identifier helps us to know whether that actually these are TCP retransmissions because they've got a different IP identifier. It's a different packet being sent out by the TCP stack, the IP stack. And that's useful when, as I say, when we were looking on the wireless side, because you can see that wireless retransmissions, the IP identifier is the same. And then when we see the same packet, but of the TCP retransmission, that's going to increment. So it's just a nice little way of spotting that. So shall I show you my last example? And then a little bit simpler.
So one quick question before you go there, though. Another question here from the crowd. So this one is from Chris, and it's related also to decrypting. And he is asking, can you decrypt Wi-Fi traffic if you use 802.1x authentication and not PSK?
That's a great question. The short answer would be no. Is it possible at all if you're really, really clever and you mess around for ages? Yes. But let me tell you what you need, and this is your problem. If I just go to decrypt wireless and packets, and this is just a lab one I use in some of the courses I teach, so I'm not giving away any secrets here. I use the pre-shared key password, and my SSID is lab4. But these two generate something called a pre-shared key, which would be effectively to powerize master key. When which is a 256-bit key. When you're using 802.1x, that same key is generated, but through the 802.1x exchange. It comes from what we call the AAA key, which is a key passed from the radius server to the access point. Now, and I can, if I want to, just type in, you'll see in here that 200, if I don't know it, I could type in the 256-bit key. So here, if I know that key, I can type it in hexadecimal, okay? So if you could find out what that AAA key was, if you could, and it's per user per session, so it changes every 4-way handshake. So for a particular client where you've captured, if you knew what that key was, you could decrypt their traffic. The problem is, how do you get that key? And that's the problem. And some, wireless LAN management systems don't readily give that up because that would be a security issue. You can, and I have done this just to prove that you can do it. If you had a wired capture going between the radius server and the AP or the wireless controller, and you captured the radius access accept, and you had a wireless capture going, so you captured a 4-way handshake, and you knew the radius shared secret, which is what the key is encrypted in, from the wired capture, you could use a radius shared secret. You'd have to know it to decrypt the AAA key, which you could then get the pairwise master key from. You could then put it in here. You'd have to have the 4-way handshake for that one session, and you could decrypt the traffic. So can you do it? Yes. Is it easy? No.
Well, there you go, guys. Just in case, don't try that at home. So
yeah, you can try it at home, but ordinarily the answer is basically no. But there's always ways around these things if you really need to.
We have a few other questions here, Peter, for you. So from German, you have to differ between a missing TCP ACK and a selective TCP ACK (SACK). When no TCP ACK comes back, the sender will retransmit after 3, then 6, then 12 seconds. A selective, I think they meant there, TCP ACK points at the bytes that are missing, and the sender will retransmit those at once. I guess it was more of a comment, that question though.
Yeah, that's I think more of a comment, but yeah, that is right. So yeah, so you do see, I don't know what's been used. I think it was just send the TCP. Yeah, it was. There's no, but you will see sometimes them using selective acknowledgements, and you get a little extra bit of information. It's not using selective acknowledgements here. So I can't really show that in this example, but where it can just tell you which bytes it's missing, whereas traditional TCP acknowledgements just say, I've got data up to this point, and you don't have to retransmit everything after that point.
Yep.
Yeah. Perfect.
So one more question, then we move on, guys.
Yeah.
So from Joe, could you, with Kali Linux, retrieve that key? I guess
well, again, the only way really with it would be the same principle. However, whatever tool you're using, really, you'd need to sniff both the radius traffic to get the key. But you can do that by basically sniffing the radius, but you need to know the radius shared secret. So without knowing the radius shared secret, no, you can't. You'd have to know the radius shared secret and sniff the radius protocol.
Okie doke. Well, thank you, Peter. Now let's move on to the last example.
Yeah, so the last example I thought would be a bit of a fun one, because we did say we would talk about QoS, which we've not talked about to this point. But instead of looking at wired trace files to identify wired issues, I thought, why not look at identifying a wired issue from a wireless trace file? Just a wireless trace file. I thought that might be quite fun. And do a QoS example as well. So this is, again, it was a customer. They had voice calls and they were having problems with internal voice calls. They all used laptops with, it was Skype for Business they were using at the time. And they were sometimes getting problems in one direction on a call. And so we were, and particularly happening around one area. So we had, I was in the capture of someone on a phone in the area, and the other person was on another wireless voice phone, but on another floor in an area that worked well. So that was the situation we were in. And I've got the traffic here. Now, the voice traffic was using, this was encrypted Veta 2.1x, the ETLS, so it's all encrypted data. I can decrypt it. So we're in that situation where I can decrypt it, but all the voice traffic is going to be encrypted data. It's not going to be like beacons. So sometimes what I like to do is just say, if I'm looking at a particular problem, is I'm just going to select all the encrypted data frames, because that's what I'm really interested in for this particular problem. So I'm going to take all the encrypted data frames and I'm just going to put them in a new tab inside OmniPeak, because that's just it's a quick way of filtering, really. So now I've got just the encrypted data frames here. And you can see I've got voice phone 1, voice phone 2. Again, I've color coded by source. So anything coming in green is coming from voice phone 1. Anything in blue is coming from voice phone 2. So if I look at this path, packet voice phone 1 to voice phone 2, we can see here that a couple of things that's interesting to see. This is going to the distribution system. So this is coming from source voice phone 1 and it's going towards the access point. So this was a phone we were looking at. And I can see it was tagged as voice in the cross control field. So I know this is actually, it's not a data packet because it's a laptop, it could have been something else, but this is actually one of the voice packets. Okay. And that's what I'm interested in. So I'm going to again take this and I'm going to put it as a column because that's going to tell me, and I'm going to just slide, let's pull that, find that column, and I'm going to slide that along back to where I can see it a bit more because I've got lots of columns opened here. So now what we tend to see when we see a voice phone call between two phones, you're going to have, let's say we're using G711 at the encoder, that encodes 20 milliseconds of voice. So every 20 milliseconds in each packet, 20 milliseconds of voice each packet. So every 20 milliseconds I need to send a frame, that's my voice going, and I need to receive one coming back. So it's quite normal when we're looking at the voice phone packets, that's the green and the blue ones, to see blue, green, blue, green, blue, green, blue, green. These are like the every 20 milliseconds we're getting a packet. And you can see the size is the same, 138 bytes. It's carrying that 20 milliseconds voice. So these are my voice packets. But now I've put this column on, what do we see? Voice, bets effort, voice, bets effort, voice, bets effort, voice, bets effort. You see, what we really want to do is see them all tagged as voice. These are my voice frames. What we can see is the ones going from the wireless client going towards the AP are being tagged as voice. But the ones coming back from the AP are being tagged as bets effort. Now, when we happen to do a capture in another location, which was the location of the other phone, and there we saw voice. So, which again was interesting. So I've probably got that packet capture, but the interesting thing about it is that there was voice. So what we realized was that the voice phones are tagging the traffic correctly. When they leave the voice phone, they're going out as voice. So you can see here voice, every packet's marked as voice. This was the other end of the conversation. But we'll go back to the problem trace file. But for some reason, by the time the phone was getting from the AP coming to the client, it had been set as bets effort. And that was happening in this area coming from this AP, where all the problems were occurring. So what it led us to believe is that somewhere on the wired network, tagging was being, QoS wasn't enabled on some port, and what we actually realized was it was a switch that all the APs in its area were connected to. What we actually found out, it was no longer, it didn't have any QoS enabled on that switch. So all the priority was being lost on the switch connected to these APs, and that's why they're all coming out best effort. So that's just a nice example of looking at just a wireless trace file, but detecting a wired issue.
Yeah, that's pretty interesting. And from what I've heard, it's a fairly common problem
Hmm.
where it's only one piece of the network, like in this case, the switch, that someone forgot to enable QoS, and that basically impacts everything else afterwards. And this one, I like it that you can, for example, put the QoS control field in there, because that's one of the first things I noticed right off the bat. Right off the bat, it was voice and best effort. Shouldn't it be voice, 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 voice? Like, there's something weird right off the bat in there. So that's a pretty easy way of seeing that there's a problem in there indeed.
Yeah,
So,
and the nice thing to point as well is this is all encrypted data, so we can decode the data, but the MAC header is always unencrypted. So even though, yeah, we can decrypt it, I can still troubleshoot it from information in the MAC header.
Nice. Okay, though, Peter. So there's one more comment in here before I guess we finish this session for today. And I guess it's more of a kudos from David. He's like, hey, another question, but thanks, Peter. You may be the only guy on earth who can make packet captures fun. So
Brilliant.
yeah, man, I agree with that. It seems to be has been a fairly interesting session. So guys, well, as you can see, TCP and QoS can cause, even if there are technically problems on the wired side of things, could cause an after effect that may reflect as a Wi-Fi problem for the end user. And that happens a lot, as we mentioned earlier. And so basically, hey, always keep in mind that not every supposed wireless problem is really generated on the Wi-Fi side. It could be on the wired, or like on the second example here, it could be on both. It could be a mix of a lot more than one thing in here. So another question, let's see here, from German again. For this AC category mismatch, it will well only be negative if the network was higher load.
Yeah, of course. If you've got not a lot on your network and it doesn't need to prioritize voice because there's not a lot of data traffic, then you're not going to see that impact. But this was a very busy enterprise environment with big, it was all big open office areas. There was 200, 300, 400 people sat in each area. So there was a lot of, and everyone connected. The other thing to say about this environment is everyone connected Wi-Fi. There wasn't even wired connections going to the desks. It was a wireless only office, so it was busy.
In reality, if you ask me, best practice, at least in my opinion, even if the network is not as busy, you should still try to configure your QoS. It'll give you better performance anyway. So
absolutely.
So anyway, guys, I think we're running a little short on time. Still, if there's any final questions, feel free to type them in, and we'll answer those for you. So I don't know, Peter. Meanwhile, will we wait and see if there's anything else or any other questions? Anything else you want to add before we finish today's session?
I don't think so, really. What I would say is, obviously, people have said that protocol analysis, I make it fun, but it is fun. But the thing to do is just to, if you don't do a lot of it, then I would say just practice, capture packets, have a go, have a play. That's how you learn, just by doing it. And it's amazing what you'll see. You'll find all sorts of interesting things as you start looking at protocol transfers.
Well, there you go, guys. Packets ain't boring. So now you know it. Okay, it seems like there's no more questions for today. So if that's the case, I want to thank everyone. Peter, thank you again for joining us today. A great session. I hope you will join us again in the future on another episode of Tech Chat. And as for everyone here, all of you, thank you again for joining us for NetAlly's Tech Chat. And hey, I'll see you all next time.
Cheers, see you next time.